This is problem 66 from chapter 15. Block A, having a mass m, is released from rest, falls a distance h, and strikes the plate B having a mass of 2m. If the coefficient of restitution between A and B is e, determine the velocity of the plate just after the collision. The spring has a stiffness of k. So first, we're going to find the velocity of A at the start of the collision, so at the moment that A hits B. This distance is given to us as h. We're going to find the velocity of A at the start of the collision by using the conservation of energy. The kinetic energy of block A to begin with is 0. The gravitational potential energy of block A to begin with, if we say our datum is here, it's starting from a height h, so that would be the mass of A, which is just m, times g times h. As block M falls, up until the moment that it hits block B, there's nothing touching block A, so there are no forces on block A other than the force of gravity. So the work done by other forces is 0. Then we have the kinetic energy of block A after the collision plus the potential energy of block A after the collision. So now block A is at a height 0, so the gravitational potential energy is 0, and the kinetic energy is 1/2 times the mass of block A, which is just m, times the velocity of block A, which is VA2 squared. So now we can say VA2 is equal to, multiply both sides by 2, and the m's cancel out, and you have the square root of 2gh. And block A is moving downward, so if we say up is positive, this is negative square root of 2gh for the velocity of A at the start of the collision. Now we're going from event 2 to event 3, which is right after the collision. So let's say from 2 to 3, which is during the collision. We're going to use conservation of energy. Oops, not conservation of energy. We're going to use conservation of momentum. And using the impulse approximation, we have no impulse acting on the system of A and B during the collision. And so we have mass A times the velocity of A, which is negative square root of 2gh, plus the initial momentum of B, which is 0, and then this is equal to the mass of block A times the velocity of block A after the collision, so we'll call that MVA3, and then we have the mass of block B, which is 2m, times the velocity of B after the collision, so that would be VB3. Now we have two unknowns in this equation. So we're going to get a second equation by looking at the coefficient of restitution. The coefficient of restitution is VB3 minus VA3 over VA2 minus VB2, where these are the initial velocities and these are the final velocities after the collision. The coefficient of restitution is given to us, that's E. So E is known, and I don't know VB3. I don't know VA3, but I do know VA2. This is negative square root of 2gh minus, for the initial velocity of B, that's 0. So I have VB3 minus VA3 is equal to negative square root of 2gh times E. So now I have a second equation, and I can take these two equations and I can solve them for the final velocities. So let's take a look at what I have here. I have VA3 and VB3. Well, if I cancel out my mass, which appears in every term, then I can take, let's call this equation 1 and equation 2, and add them together. So I'm going to do 1 plus 2. Equation 1 is this negative square root of 2gh is equal to VA3 plus 2 times VB3. Equation 2 is minus E times the square root of 2gh is equal to VB3 minus VA3. Then add both sides together. VA3 minus VA3 gives us 0. VB3 plus 2VB3 gives us 3VB3. And over here, we have a negative square root of 2GH times 1 plus E. So we have VB3 is equal to negative square root of 2GH 1 plus E over 3. And then using, let's say, equation 2 to solve for VA3, we get (2GH) times 2E over 3 minus 1 over 3. And you can check that on your own. So those are the solutions, and we're going to talk about what the solutions mean. So now we just want to check to make sure that our solution makes sense. So we have the velocity of B after the collision and the velocity of A after the collision. And we said that positive was upward. So if the sign is positive, the object is moving upward. If the sign is negative, the object is moving downwards. So E should be somewhere between 0 and 1. We're going to look at the extreme cases here. If E is equal to 0, it's a plastic collision, and the objects should stick together and be moving together after the collision. If they're moving together, they should have the same velocity. If E is equal to 0, for VB3, you get negative square root of 2GH times 1/3. That comes from this. And for VA3, you have square root of 2GH times 0 minus 1 over 3. And this is equal to this. So they are moving together. So that looks good. And they're both moving downward in this case, which makes sense since A was moving downward to begin with. So they both move downward, but at a smaller velocity than A had to begin with, because now you have more mass. If E is equal to 1, the collision is perfectly elastic and energy should be conserved. So we want to check to make sure that energy is conserved in this case. Here's the velocity of A right before the collision. So the kinetic energy that we had right before the collision would be 1/2 the mass of A, which is just m, times the velocity squared, which is 2GH. If energy is conserved, we should have the same kinetic energy after the collision, but now we have two objects moving. We have A and B, which are both moving. So we have 1/2 times the mass of A times the velocity of A after the collision, and if E is equal to 1, this is 2 minus 1, which is 1, so that's square root of 2GH times 1 over 3 squared. So this is the kinetic energy of A after the collision. The kinetic energy of B after the collision is 1/2 times the mass of B, which is 2m, times the velocity of B after the collision. If E is equal to 1, this is 1 plus 1, so this is negative square root of 2GH. 1 plus 1 is 2, so this is over 2/3 squared. This gives us 1/2 m times 2GH times 1 over 3 squared would be 1/9 plus 1/2 times 2m times 2GH times 2/3 squared, which is 4/9. I can pull out a 1/2 m 2GH. If I pull that out from the first term, I'm left with a 1/9. If I pull that out from the second term, I have 1/2 m 2GH. I have a 2 here and a 4 here. That leaves me with an 8/9. 1/9 plus 8/9 is 1. So this is 1/2 m 2GH, which is the kinetic energy that I started off with. So that checks out too. In this case, if E is equal to 1, if we go back to our equations here, we have 2E minus 1. So A would be moving upward after the collision, and B would still be negative and moving downward after the collision. So if E is equal to 0, they both move down. If E is equal to 1, A moves upward and B moves downward, and you could have anything between 0 and 1 for E. And that concludes problem 66.